Welcome to Lecture 2.5 on Structural Phase Transitions and Stability, part of Module 2, Introduction to Perovskite Materials. In the previous lectures, we discussed crystal structure, bonding characteristics, and optoelectronic properties of halide perovskites. Today, we shift our focus toward structural stability, specifically, how and why these materials undergo phase transitions. This lecture is fundamentally about understanding instability from a crystallographic and thermodynamic perspective. We will analyze three major phenomena: structural polymorphism, moisture-driven lattice degradation, and light-induced halide segregation. Rather than treating them as isolated problems, we will examine them as manifestations of lattice energetics and ionic mobility. Let us begin with structural phase transitions. Polymorphism is the ability of a material to crystallize in more than one structural configuration while retaining the same chemical formula. Our model system today is formamidinium lead iodide, or FAPI3. At elevated temperatures, FAPI3 adopts the black alpha phase. This is the cubic perovskite structure consisting of a three-dimensional framework of corner-sharing lead-6 iodide octahedra. This 3D connectivity is essential. It enables strong orbital overlap between lead-6p and iodine 5p orbitals, producing favorable band dispersion and efficient charge transport. However, at room temperature, this cubic alpha phase is not the thermodynamic ground state. Instead, the material transforms into a yellow delta phase. This delta phase is hexagonal and contains phase-sharing octahedral chains rather than a 3D network. The change in octahedral connectivity dramatically alters the electronic band structure. The material becomes optically inactive for photovoltaic purposes and essentially insulating. This is not a chemical decomposition. No atoms are lost. Rather, the lattice reconstructs itself to reach a lower free energy configuration. This is a purely structural phase transition. So the key question becomes, why does the cubic perovskite structure become unstable at room temperature? To answer that, we must examine the geometric constraints of the lattice. The stability of the perovskite structure is governed largely by ionic size compatibility. This is captured by the Goldschmidt tolerance factor. The tolerance factor, T, is defined as T equals the sum of the ionic radii of the A-side cation and the X-side anion, divided by the square root of 2, multiplied by the sum of the ionic radii of the B-side cation and the X-side anion. For a perfectly cubic perovskite, T is approximately equal to 1. If T is significantly less than 1, the octahedra tilt strongly. If T is greater than 1, the lattice experiences expansive strain. Now in FAPI3, the A-side cation formamidinium is relatively large. This pushes the tolerance factor slightly above unity. Even a small deviation from 1 introduces internal lattice stress. The corner-sharing octahedral framework becomes geometrically strained. To relieve this strain, the structure reorganizes into the hexagonal delta phase, where octahedra are arranged differently, and the geometric mismatch is reduced. So the alpha to delta transition is fundamentally a geometric stabilization process. The lattice sacrifices electronic functionality in order to minimize structural stress. This highlights an important principle. In crystalline solids, structural stability is governed first by lattice energetics, not by electronic performance. This geometric constraint is why compositional engineering, such as mixing Fa with cesium or methylammonium, can stabilize the cubic phase by adjusting the effective tolerance factor. We now move to chemical instability. Hybrid perovskites contain organic cations that interact with the inorganic lattice via hydrogen bonding and electrostatic interactions. When water molecules diffuse into the film, they disrupt these interactions. The simplified degradation reaction results in the formation of lead-2 iodide and volatile organic species. The volatile components escape, leaving behind crystalline lead-2 iodide. You may often observe yellow patches forming on degraded films, that is, lead-2 iodide. Mechanistically, water molecules penetrate primarily through grain boundaries and surface defects. Because perovskite films are polycrystalline, grain boundaries act as fast diffusion channels. Water lowers the activation barrier for bond dissociation. Importantly, water frequently acts catalytically. It is not necessarily consumed in the reaction. Instead, it assists in bond cleavage and then diffuses further into the lattice. Thus, even trace moisture, at parts per million levels, can gradually degrade an entire film over time. From a materials science perspective, hydrolysis is fundamentally different from polymorphism. Polymorphism preserves chemical composition. Hydrolysis irreversibly destroys it. Therefore, encapsulation strategies and interface engineering become critical in practical device design. Now we turn to a more subtle but equally critical instability, the Hoek effect. This phenomenon was first systematically reported by Elizabeth Hoek in mixed halide perovskites. To tune the band gap for tandem solar cell applications, iodide and bromide are alloyed within the lattice. In the dark, these halides remain homogeneously mixed. However, under continuous illumination, something remarkable occurs. The halides segregate into iodine-rich and bromine-rich domains. This segregation is reversible once illumination is removed, indicating that the phenomenon is kinetically driven. So what drives it? Photo-generated carriers interact strongly with the lattice. Carrier-phonon coupling induces local lattice distortions. These distortions generate strain gradients. Strain gradients lower the activation energy for halide ion migration. Once ions become mobile, they diffuse and nucleate compositionally distinct regions. The iodine-rich domains possess a smaller band gap. Electrons and holes preferentially recombine in these regions. As a result, the open circuit voltage drops significantly. So here we see a fascinating paradox. The very act of generating carriers under illumination activates a degradation pathway. This reveals the intrinsically ionic nature of halide perovskites. Their relatively low ion migration barriers, which contribute to defect tolerance, also make them vulnerable under operational stress. The intensity of halide segregation depends strongly and non-linearly on photocarrier density and exposure time. The empirical kinetic model shown in the slide captures this relationship. Segregation intensity increases with carrier generation rate and saturates over time. Physically, this tells us that higher illumination intensity accelerates ionic redistribution. In other words, the material's stability is linked directly to carrier density. This is highly unusual compared to conventional semiconductors like silicon. In halide perovskites, electronic excitation and ionic motion are coupled phenomena. This coupling is central to understanding long-term operational degradation. Let us now synthesize everything. We have examined three distinct instability mechanisms, each governed by different physical driving forces. Polymorphism arises from geometric lattice strain and thermodynamic free energy minimization. Hydrolysis arises from chemical reactivity with water and bond destabilization. The Hooke effect arises from photo-induced ionic migration and carrier lattice coupling. All three mechanisms highlight a central theme. Halide perovskites are soft ionic crystals. Their structural flexibility enables exceptional optoelectronic performance. But that same softness introduces vulnerability. Therefore, any stabilization strategy must address geometric lattice mismatch, environmental protection, and suppression of ionic mobility. In the next part of this lecture, we will explore how compositional alloying, interfacial engineering, and dimensional confinement are used to combat exactly these structural weaknesses. Thank you for your attention.